see my slides, I guess.
Right. Okay, very good. So we'll continue with Sven Krippendorf of mining symmetries of string vacua.
Yeah, thank you, Mike. Let me also start by thanking the organizers to bringing together our community this year online, and to tell you, thanks for the invitation to tell you about our work. So this talk is about finding symmetries of string vacua in two different ways. Firstly, I want to talk about finding finding symmetries with the help of human power. So this is based on a paper which will appear later or early next week. This is a very long paper, and I cannot talk here about everything which is in there, unless I would talk in a style like Nima for 12 hours. So this is just a short advertisement. Secondly, this talk is about finding symmetries with the help of machine learning. And these are collaborations with students here in Munich, Max Ferry and Philipp Etzler. Okay, so let's get started with looking at symmetries using human power. So the prevailing topic in string phenomenology over recent years has been to discuss the viability of effective field theories we obtained from string theory. And this has clear implications for building de Sitter vacua or models of inflation in string theory. Another old question in string phenomenology is obviously the search how low energy pattern in effective field theories arise from strings. And by now we have many candidates for trustworthy effective field theories we all love, such as KKLT or the large volume scenario. And we also have many conjectures about them with relevant and sometimes irrelevant phenomenological consequences. And so this part is about this topic. And when this approach that we're talking about is always good to look at other areas in physics where this has happened before. And this is actually a problem which is not really new in physics, and it has appeared before in many contexts. One of them is, for instance, looking at things like chiral perturbation theory. And we really know how to deal with it there. So firstly, I mean, we could, one approach is to calculate processes in UV using lattice QCD, or in our context directly in 10 dimensions. The other approach, which works very nicely in chiral perturbation theory and other areas of physics, is to identify symmetries of the UV and write down the effective field series consistent with it. And then we use approximate symmetries to use organizing principles of our effective field theory and write it down. Now, the main message from chiral effective field theory is that even if you have like approximate symmetries that can be used to organize the effective field theory. So if you think about the quark masses, you start by start with something which is breaking the SU3 from Gell-Mann from the start work. Yeah? Nevertheless, we have pions as the Goldstone modes of this symmetry, and they really organize the low energy effective field theory. So the question we want to ask in this part is, how can we use approximate symmetries of strings to organize our effective field theory and to make generic predictions based on these symmetries? In the second part of this talk, we'll develop some methods to automatically search for these symmetries. So you might wonder, what would be these approximate symmetries in strings? This is a very old story, bringing us back to the early days of string theory. And scaling and shift symmetries were identified in 10-dimensional supergravities. To give you just a glimpse of these, let's look at the heterotic string, where the following two classical scaling symmetries can be identified. Such scaling symmetries feed then down, and it's very well known, to the four-dimensional effective field theory. And it does happen that the exponential of the Kähler potential, so e to the minus k over 3, becomes then a homogeneous degree of one function. And this implies that the Kähler potential is of so-called no-scale form. And clearly from the start work, these are not exact symmetries. They're broken by alpha prime cube corrections, for instance, which were famously, for instance, calculated here by Becker, Haag, and Louis. And but nevertheless, given the success of chiral perturbation theory and other effective field theories, I want to ask, what can we actually do with them? Before we do this, let's look at a little bit the power of these scaling symmetries when looking at some basic phenomenological properties. The first observation is really that such scaling symmetries immediately imply the absence of de Sitter and anti-de Sitter minima. So if you scalar potential scales, you can see the vanishing of the gradient of the potential immediately implies the vanishing of the scalar potential. And another thing we've seen over the years, various times, is really miraculous cancellations when we explicitly calculated certain phenomenological properties, such as soft scalar masses, etc. And one, for example, there's really is when we calculated the soft scalar masses in a large volume scenario, is that they can really vanish if the Kähler potential takes a particular form shown here, particularly the Kähler potential for the matter fields. And other striking features that we have include the generic mass that we have for our pions in the game, which are the breathing mode and the dilaton. And here they are both hierarchically below the KK scale. One more elaborate picture is this one. So no scale is not equal to no scale. So there have been various things in the literature. Here we organize these various types of no scale, which have appeared over the years in several nested categories. And I think this is a very nice summary. So this allows us to understand why various models, which at first sight might violate some classical no scale condition, still have a vanishing scalar potential. And it's really rather intriguing when you do the explicit analysis to see how various modular effective field theories fit into these larger categories of no scale. Yeah? And this allows you to even be protected if your radiative corrections, say, violate one of these conditions, for instance, this condition here, but preserve then more general categories. So you might wonder, okay, so how can this happen? Well, this really happens when we're looking at a situation where the loop counting parameter is itself a scaling field. So for instance, here the breathing mode is such a scaling loop counting parameter. We firstly have like the standard expansion in the counting parameter. However, the scaling symmetry dictates the tree-level dependence, like this one here. And this implies immediately that the one loop term does not depend on the breathing mode. And you can immediately calculate also what the consequence is that a generalized no-scale condition is not violated, and the potential enjoys an unexpected suppression. And exactly this suppression mechanism we do see realized when we organize a string effective field theory according to the respective loop counting parameters. So we identify them explicitly. So for instance, in the heterotic, this is like t cubed over s and 1 over t. And then the masses of our quotation mark pions are generated by the breaking of these symmetries. And the mass really depends, as usual in this kind of analysis, on the spurion fields, which give them a mass. So an example of a spurion in this context would be W0. But they are obviously also constrained to appear in the appropriate invariant combinations under the scaling symmetries. So here, for instance, this is the invariant scaling combination that we find in type 2b as W0 squared divided by G string 1/2 volume to the 2/3. And so this obviously can be small, and that can validate your effective field theory. Now, before showing you results on the scaling symmetries, let me show you very briefly how you deduce the scaling of the Kähler potential and the superpotential from a scaling symmetry. So you work with the action at the two derivative level, for instance here for concreteness. And so where phi is our chiral compensator. And now let's say we have some scaling, yeah, that we've found. We'll see this explicitly in stringy effective field theories, that we can find exactly such a scaling of this. So we have a scaling of this type. Now, the scaling of the superpotential and of the overall Lagrangian fixes then the scaling of the compensator. And subsequently, this fixes the scaling of the exponential of the Kähler potential. Yeah? So that obviously fixes then the scaling of this term. And so if you pick an example here of certain weights, which we actually see realized, is that this fixes the scaling behavior of K. And this is precisely of a scaling of the no-scale condition, which I showed you earlier as kind of the smallest category of these no-scale models. Now, let's go concretely to string theory example. In the paper, we discuss heterotic type 2A and type 2B. Very explicit. So here, I want to give you an example of type 2B with the inclusion of localized sources. We identified two scaling symmetries. One is an element of SL2R. And I'm displaying you the scaling behavior here in both in 10D and then in 4D after dimensional reduction. What do you find? Now, this is good, but now the crucial part is obviously, okay, so how can we use this to organize our effective field theory? And we can really use this then track the expansion of our effective field theory of some general higher order correction in terms of the true expansion parameter, 1 over imaginary parameter of tau, and this combination of tau and the volume. And this organization of the corrections, you can write down, say, for a Kähler potential, superpotential, Lagrangian, and you have the tree level term, and then you have higher orders, right? So obviously it's contained there, and this ANMR is a scale invariant coefficient here. So some of you might have already spotted that localized terms, when we're thinking about V-brains, scale actually differently compared to the bulk terms. So this is not inconsistent with the picture. The brain terms, for instance, in tree level, just take the DBI one, they scale in such a way that they appear in the classification here at higher order. So that's one can nicely find how they appear. Another point you might have wondered about is, okay, how do these results match explicit calculations to corrections in the literature that people have done calculations from 10D. And in the paper, which I cordially invite you to read, so we go through the detailed exercise of matching them, and we find perfect agreement. And another advertisement for more details in our paper is to take some detailed look on a story about how we treat matter fields, how they are constrained to appear at lower energies. We show that there is some intricate interplay between shift symmetries connecting axion fields of the moduli and the gauge potentials. These symmetries naturally appear in the context when you start talking about higher form fields. So as this is the first part, and before I go to the machine learning part, let me summarize this part for you. So the main message here is really, I want to give across, is that the structure in the effective field series from strings can really be traced back to approximate symmetries in 10 dimensions. This includes scaling symmetries, supersymmetry, and generalized shift symmetries. And these specific UV completion properties lead then to generic predictions at low energies, following just simply applying the rules of effective field theories. And this UV structure, symmetries, separates and string effective field theories from ordinary effective field theories without the UV completion. Properties which naively might be thought of as model specific are then in fact can be traced back to generic symmetry consequences in these string UV completions. And it's very exciting because it links like really general string theory UV properties, such as duality, symmetries, to generic phenomenological properties. Yeah. I think that's a really nice link that we can explore. And another really thing why I think this, it's a very interesting perspective, is that the story we are telling here is very analogous to another success story of effective field theories, namely carrier perturbation theory. And I think these can be really used as nice guidelines on how to proceed even further here. I've already identified here several underlying symmetries and looked at their consequences. And it's really, spurions, for instance, we can identify, and we have here the flux superpotential and non-abelian couplings appear and trace them in invariant combinations. And they can be parametrically small, which is, then allows you to completely justify certain effective field theories. We can obviously match with ab initio calculations. So here, which is kind of the equivalent of lattice calculations that you do in carrier perturbation theory. And I think this is very exciting for the future, as we have a framework here which lets us work out generic low energy consequences of string theory. And we kind of systematically can check for phenomenological models, which we then have missed before, as we, and we can trace then also the low energy consequences of these, say, duality symmetries back, to phenomenology. So this is the first part of my talk of, using human power to look at symmetries, and now I turn to using symmetries using computers. So we have just seen an example, obviously, that knowing about symmetries of your data is very crucial to understand it. And what we want to ask here is whether we can automatize this search using neural networks. One way of phrasing this concretely is to find the symmetries leaving a function such as the Lagrangian or so invariant. And a crucial part of this program is not just to find such an invariance, say, but also then to identify which symmetry it corresponds to. In our work, we address rediscovering known symmetries for now. And so this includes like looking at the potential function, but also very nicely, like we look at discrete symmetries appearing in the context classifying Calabi-Yau manifolds. And we can also connect these physics setups to actual like real-world high-dimensional data of images. So we have seen that symmetries give organizing principles for effective field theories. In the realm of machine learning, efficient neural network architectures are also, heavily relying on symmetries. One prime example is, say, the invariance and the translation that come to your mind when you think about convolutional layers. But also other symmetries are seeing success stories. So if you're thinking about networks which implement invariance and the rotational symmetries, give you state-of-the-art performance in medical imaging segmentation, for instance. So here we want to find these symmetries without really domain knowledge. And speaking about the previous part is really, if you don't know a symmetry, or don't know about what the underlying symmetries are, you want to have a method that finds them without knowing them. And this is a problem which is also not known in machine learning to address, but obviously of great interest to utilize symmetries as much as possible. What we'll see is that these techniques are very good at mapping similar data points together. And I find this really interesting to address questions like, looking at, constructing something which is, a periodic table of Calabi-Yau manifolds, just to give you a bit of a perspective. And also, this is, I think, very good when you're thinking about, want to think about sampling vacua with distinct properties, because as soon as you put in your sampling algorithm the underlying structure symmetries of the problem, you immediately get more stability. And obviously also has some connections when people look at simulations of dynamical systems, etc. They also want to build in symmetries. Good. So let's ask, how can we use neural networks to detect symmetries? The basic observation, which we'll use here, is that the representation of data become more and more meaningful in deeper layers of your network. And data sharing the same properties is grouped kind of together. Fabian already mentioned exactly the same concept. It's the same thing that's happening. It's like, it's, you know, here for instance, if you look at things like word to vector, where you embed words of close semantic meaning, they're that closely in latent space. So, like as Fabian had, I have a different equation here, but it's the same thing. So you have, this becomes meaningful to say something like England minus London equals Paris minus France, and that's a concept we want to use. This has actually found other applications in science. So this concept has been adapted to recover things like our well-known classification of atoms in the periodic table. And the authors use just names of molecules for this classification. Another interesting application has been in the classification of scents of molecules, where the authors use some graph embedding of molecules to study and predict their properties. Now, this seems to be good for finding common structures. So what we did, we wanted, to see whether this can be applied to detect symmetries in physics. And we find that we can indeed find symmetries in this way. So we implement this in 2 steps. Firstly, we find the invariances. And then in the second step, we identify which symmetry is really responsible for the invariance found in the first step. So how do we find the invariance in the first step? Well, we set up a classification problem, here based, for instance, on the value of the potential or the Hodge numbers. And once we have trained our neural network classifier, we can then analyze the position in the embedding layer. So we do this directly or by applying appropriate dimensional reduction, as you will see in a second. In the second step then, we identify the symmetry by analyzing the nearest neighbors in the associated point cloud of invariant data points. To this, we apply dimensional reduction again if necessary, and these neighboring points contain the information about generators of the symmetry group. And to identify the components of the generators, we need to then identify the appropriate regression problem to actually do this. I'll explain this, how we do this in a second. First, let us look at the first step now. Second. Probably the simplest example we can think of is a standard fixed potential. And now what we have to do is we have to translate this into a classification problem. And this is simply done by picking discrete values of the potential. So something like you have discrete classes like shown as here. But the crucial thing is obviously there are points in this which correspond to the same class, but they're not related by the symmetries. And looking at such structures and structures where this doesn't happen allows us to have a look at whether the neural network actually finds some symmetries and is using them. So here's the setup. So we pick a standard feed-forward neural network with several dense layers for the classification, something like here. And then what we do is we look at the second to last layer. So this is what we call the embedding layer. This is the one just before doing the classification. We train the network easily to some decent accuracy. As Fabian was also explaining nicely, you can actually, that's not a problem. And then we look at the embedding. So in principle, this is 80-dimensional, and we have to apply some dimensional reduction to this. And this is shown here. We apply stochastic neighbor embedding on it. And now you can have a look at where things are mapped, in this space. And when you look at it carefully, you see that points on these islands are related by symmetries, first of all. And for all classes with 2 different radii, we find 2 islands in this embedding. Yeah, so for instance, as I'm showing here, whereas for points, whereas points which are not related by a symmetry, they're mapped together. So like this, this yellow one here. And we see the same behavior also for an example with SU2, which we discuss in the paper. Okay, now. So now let me show you another example, which is obviously of interest here, is we're looking at the case of complete intersection Clavier fields. So a classification has been performed here, famously in 3 and 4 dimensions. Symmetries in this context really refer to different configuration matrices, which describe the same manifold. Here is an example of what is meant by a symmetry. A priori, these identities are not known, and it requires some effort to show these invariances. However, they are crucial to make a classification of these matrices. And when we did this, there is another obstruction which we encountered. And this is that, all these configuration matrices, they're basically invariant under permutation. Now you want to deal with this in the neural network such that, neural network is not struggling with this. So one way to do this is by using a graph representation of the configuration matrix, because this is more tractable. So we use some graph embedding of this. And yeah, so what we put in is the different types of nodes and the eigenvalues of the adjacency matrix. Then as a classification problem, we here have the classification of Hodge numbers, H11, H12. And in this list of 3D CCs, there are many examples which share the same Hodge numbers. And I think it will be interesting to see whether our method is able to distinguish them from each other. And here are our results. So we created samples for the 3D CCs. And again, we use a standard feed-forward network for our classification. Then we examine this embedding layer again. And now there are too many classes to perform a visualization. And instead, what we do is we look at the nearest neighbor. This is shown here on the right. So we will plot the distance of the nearest neighbors for one sample. And you can see that there are several jumps, yeah, that you can see. So we can look at the difference of this. And we then take simply the largest of these jumps as our cut to keep the data points all in the same class. And all configurations in this red region are taken to be the same Calabi-R. We can test this cut on the performance, and we find very good accuracy. Here are the results. And although the network has only the information about the Hodge numbers, it's really able to distinguish between CCs with the same Hodge numbers. Yeah, so this is shown here. And an interesting question is really clearly, which properties is a neural network using to do this? Yeah, has the network secretly used some topological information as we would, normally require by, using Wald's theorem, which mathematicians have developed? And I think this is quite curious because, we're investigating obviously this connection between the theorem and the representation found by the network. Now let me briefly talk about finding generators. So the problem we face is once we have identified the invariances, we do now have the point clouds in the input space, which are related by some symmetry transformation. So you have some point cloud. You essentially want to identify what is a generator to do this. Out of time reasons, maybe let me skip this. Basically, what we are doing is, you know that these points are related by, by standard linear relation, where T is our generator of our symmetry. Basically, we want to find something with T. What we're doing is we set up the right regression problem, which then allows us to constrain all components of T. And we do this multiple times over this point cloud. And then finally, we look at the dominant components, which is shown here. Looking at the principal components, and we really find the generators. Yeah? So that we would be thinking about. And there are some technical details, obviously, about getting signs right, etc., which is hidden here. And I'm happy to answer anything in the Slack channel on this. And also Mark, who is also around the conference. So then we can also apply this to other generators, not just SO2. So we successfully applied this for SON groups and subgroups thereof. And so we looked at, also we can apply this to images, yeah, for instance. So it's not just to low-dimensional point clouds, which we have in physics. So what we did here is, for instance, just did a little toy example where we applied this to, rotated handwritten digits, MNIST. And what do we do is, like, we dimensionally reduce this data via PCA. It looks like this. An image becomes such a point, and then we can apply our same technique as we did before. And really, what we see is in this picture is we really find one dominant component again, which is shown here. And it's, I think, a really nice example because it shows how you can apply some technique which we use to find symmetries in physics directly on data sets relevant for daily tasks in machine learning. So let me be very brief on this. So this final part is on duality symmetries for machine learning. We all know and love dualities because they're great to calculate correlators. What we really want to do is we want to look at how can we make use of these different representations. How can we use this nice tool from physics also in machine learning? One thing where this is very useful is in the context of classification. So for instance, if you think about the standard duality, high-low temperature duality in the Ising model, you have such, you want to ask a question of classifying the temperature for a low temperature sample. This is much easier when you look at it in the dual representation. So here are samples in the dual representation. You can see nicely how the data is spreading out. And we see this nicely when we perform tests on this. Now, the really cool thing is, though, how can we find such good representations automatically? And so we start with really simple toy examples like Fourier transformation. And so there, such beneficial representations are not generically adapted by the neural network. So if you start somewhere with your neural network, basically Fourier transformation we know is just a linear transformation. But when we optimize it, where the good representation is here, it never finds it. So the thing is, we can enforce this such representations by adding something to the loss to enforce it. Here we use something was based on like feature separation, and here's some picture on of the adapted representations, and it's really reminiscent of how a Fourier transformation would look like. However, you haven't told the network anything about this exact transformation. You just put some additional thing to the loss, and this then also can then be used to increase performance. Yeah, so it's not just a toy representation. It's really on this classification task you can improve. I go to another example, which I skip now, which is basically again a setup where we find that you can improve with the dual variables, and you can find them automatically. What we do here is some autoencoder setup, and what we put on is some additional loss component on the latent space. Now again, we don't tell the neural network what to do, so which representation to adapt directly. It just should perform good on this simple energy classification task, and it finds something which is resembling of these dual variables. Yeah, so and that's really nice, I think. So let me just put this into perspective. What we really start to see here is that we see how we can get dual variables without really knowing them. And I think this is nice because it provides you some new numerical avenue for finding dualities in physics. And these dualities, at least in this simple toy example, lead to improved performance. And currently, it's clearly open where this will have the largest application in daily tasks. But physics is great in the sense that we can draw from a huge pool of dualities where we can play around with and refine our techniques, apply them. And really, the way we think about dualities in this context is as kind of optimal representations of your system. So they can emerge from demanding good performance when trying to calculate correlators. So let me conclude. So we can use neural networks to detect symmetries with only limited domain knowledge. The key thing is the embedding layer, which reveals these symmetries. And we can, from these invariances, we can go to actually down to the generators. The dualities are different data representations, which we can simplify calculations of correlation functions. And this can be used for improved classification. And we can also have a handle by using this improved performance on finding them in an unsupervised way. And in simple examples, we find these dual representations. So with that, I would like to thank you and also draw the attention to this seminar series in case you're interested, which I'm organizing with Jim, Fabian, Gary, and Greg Young from Microsoft. So with this, I would like to thank you for your attention.
Thanks, Sven. Very interesting talk. We have time for a couple of questions if people. Yes, Alex.
Hi, Sven. Great talk. Thanks for it. I have two questions. One of them is, it seemed like in the identifying symmetries project, you were really getting the local structure of the symmetry group. And I was wondering if you have thought about how you might get at the global structure. And then my second question is in terms of this automatically finding dual representations, about what fraction of the state space you need to sample to get a good representation.
Yeah, thanks for the question. So this, so basically, yes, we took a really local approach here to symmetries. And we didn't think very much about global properties. Now, what we so this is true there. It's also true in the context of so in the case of the discrete ones. Okay, it's not just local, so it's like automatically. Larger transformations that you're looking at. On your second question, in terms of, okay, good. So in terms of state space that we need to find kind of these dual nice representations, there is clearly room for improvement in some sense. Yeah. So what we're using is these very toy models of Ising. So Ising 1D things, for instance, and there we can really, we use a lot of states in order to get these results. However, like you also have to see that this data is kind of cheap, yeah. So it's not some huge effort that we have to go through at this, and we're also like it's first days in some sense, yeah. So it's always like once you get it to work. I think the nice thing is really to see these representations. Now you can also ask. So I think maybe you asked this as well in terms of like when I show you these results about the representation it finds. It obviously depends on the initialization, etc., a little bit as well, right? So what kind of representation is found, and you have to do a little bit of data mining to see ones. Yeah, but the way I see this is when we look at dualities, it's like, okay, imagine you are given 100 different 100 different functions for some really cool system. Like what happened, mining through these 100 examples, you might want to do, yeah, if that gives you that good representation. Yeah.
Thanks.
Okay, thanks. I don't see more questions, so we'll stay on schedule. Let's thank Sven again for